multiplication of conjugacy classes. Let Ci and Cj be two classes of a group G. Then the class multiplication is defined as the product Ci Cj equal to the set of elements of the type AK times BL, where AK are elements of the class Ci and BL are elements of the class Cj. And in this set, we keep each element as many times as it occurs in the product. That means if AK times BL is equal to, say, some particular element dP, and the same element appears once more by the multiplication of some other, say, AK dash times BL dash, then within the set we will keep it twice. And if it occurs, say, n times, if that particular element occurs n times as a product of a type given by this, then we keep it as many times as it appears. So that's how we define the multiplication or the product of two conjugacy classes. Now, the product of two classes contains complete classes. The meaning of this statement is the following. Suppose for every element in the product, that is every element like AK times BL that appears in a product, all elements that are conjugate to that element AKBL also appears in the product. So that means if you have a particular element appearing in the class, the whole conjugacy class of it, the elements in the conjugacy class of it also appears in the product. We will now try to prove this. Let K be the product of two classes Ci and Cj. Now, the elements of K are of the type AK times BL, where AK is an element of Ci and BL is an element of Cj. Now, we need to prove that all elements that are conjugate to AKBL are also in K. So, to see this, let us construct the elements that are conjugate to AKBL. So, take X, which is an arbitrary element of the group G, and then construct the product X inverse times AKBLX. So these are the elements of the conjugacy class of AKBL. So the set of all elements of this type form the conjugacy class of AKBL. So let us try to construct this. Now we see that X inverse AKBLX is equal to X inverse AK times the identity element times BLX. Because if you insert an identity over here, the product remains the same because E times BL is BL, and therefore placing an E doesn't matter. So now E can be written as the element X times X inverse. Now we can first take the product X inverse AKX, then X inverse BLX, and then write this product as this product. But now we see that X inverse AKX is an element that is conjugate to AK. So therefore, it should be an element of the conjugacy class Ci, because AK is an element of Ci. And therefore, all elements that are conjugate to AK should also be in Ci. Therefore, X inverse AK, X should be in Ci. And similarly, X inverse BL, X should be in Cj because BL is an element of Cj. So that means X inverse AK, X is in Ci, X inverse BL, X is in Cj. And therefore, the product on the left hand side is simply obtained as the product of an element in Ci and an element in Cj. So that means that is an element of the class product K, because K contains all elements of type AKBL, where AK is in Ci and BL is in Cj. So now we have proven that any element that is conjugate to AKBL, which could be an arbitrary element of the in the class product K, and any element that is conjugate to AKBL is also an element of the product class product K. So that means all elements conjugate to any given element here should be there in the product itself. Or in other words, K contains complete classes. Okay. So now we can see that the product Ci, Cj contains only complete classes of the group, and therefore this product can be written as say the it can be separated into a collection of classes. Suppose a particular class Ck appears as say A, I, J, K times in the product Ci, Cj. And taking all those classes together, we may write this product as sum over all possible classes Ck times Aij, where Aij, are integers and they are non-negative integers that represent the number of times a particular class Ck appears in this product. So that's what I have done here. For example, if I take a product like Ci, Cj, a particular class, say Cm may appear once and Cn may appear twice, then I can write it as Cm plus Cn. That's the class Cm plus 2 times Cn. Now this is not the simple union of sets because we will be keeping any element as many times as it appears in this product. And in a set union, we write every element only once. So that's why we use this summation symbol over here instead of union. Subgroups. Given a group G, a subset of the elements of G, let us call it as H, a subset of the elements of G may satisfy all the axioms of group. And if such a subset happens, which satisfy all the axioms of a group under the same multiplication law as the group G itself, then such a group is called a subgroup of G. And it is sometimes it is denoted by the symbol, is the variant of the symbol for subset A, subset B. So this is something analogous to this one, but here H is a subset of G, but then the elements of H under the same group multiplication law forms a group itself. So H is also a group on its own. Obviously, G is a subgroup of the group itself, and also the group containing the identity element of G, that also forms a group because there is only one element. So identity is there, the inverse of identity is E, and therefore it forms a group. So there are two trivial subgroups for any group, that is the subgroup containing only the identity element and the group G itself. Now, if a subgroup H of a group G contains, if the group G contains an element that is not in H, okay, so there exists an element in G which is not in H, and if H is a subgroup also, then H is called a proper subgroup of G, and in that case we could write the notation H, this symbol G. This means it's a proper subgroup. So H is not equal to G because G contains at least one element that is not in H. Now we consider some examples. Consider the symmetry group C4V of the square we discussed earlier. And while doing this, we can also check the multiplication table for C4V. And we can see that the fourfold rotations given by C4, which is rotation by 2 pi by 4, then C4 square rotation by pi, uh, and C4 cube, which is rotation by 3 pi by 2, and C4 to the power 4, which is the identity element, and they form a group under the group composition law. And this is in fact a cyclic group. Since it is cyclic, it is abelian as well. Now, these are in fact subset of these elements are subset of the elements of the group C4V, and they form a group on their own, and therefore this is a subset of subgroup of C4V. Now C4V contains other elements mx, my, sigma, u, sigma, v, etc. And therefore this is a subgroup, a proper subgroup of C4V. So we use this symbol H and call it H1. Then H1 is a proper subgroup of C4V. Now we can also consider another subgroup, and which is, so the elements E, mx, my, and C4 square, which is also a subgroup, because as we can see, E times mx is equal to mx, then mx times mx is, so mx times mx is E, and my times my is also E, and C4 square times mx is also C4 square times C4 square is also E, and from the group multiplication table that all these operations under the composition become one of the elements of H2 itself. Now other properties like associativity already follows from the fact that C4V under the same operation is also associated. And the inverse of this is my, the inverse of mx is mx, and the inverse of C4 square is C4 square. It can be easily seen then that H2 is also a subgroup of C4V, and there are other elements in C4V which are not in this subset, and therefore it's a proper subgroup of C4V. Now we discuss cosets. So let H be a subgroup of order H of a group G, and let the order of the group G be given by small letter g. Now consider any element y of G and then construct the set of elements given by y times hi, where hi are elements of the subgroup H. So for any element y, we can construct a set obtained by multiplying y with the elements of the subgroup H, and this is represented by the shorthand notation y times H, and is called the left coset of the subgroup H of G. Now hi, so if the order of the subgroup H is say given by small letter h, then there will be H products like this in the set, and therefore the number of elements in the coset is also equal to H. So this is called the left coset because we are multiplying every element of the subgroup H from the left with y. Similarly, we can define a right coset, which will be defined like, say, hy is equal to hi times y, where hi are elements of group H. So here we are multiplying the group elements from the right with y. So now we discuss some of the properties of the cosets. First one is So we have a subgroup of G and we take Y to be an element of H itself. Okay, so if Y is an element of H itself, then the coset YH is equal to the subgroup H itself. And it is very easy to see this property, and that's because H itself is a group, and multiplying a group by any of its elements produces the elements of the group but in a different order. And this is called the rearrangement theorem, which we discussed earlier. And therefore, if we multiply the subgroup H with the elements with an element Y, which is an element of H itself, then the coset would be simply the subgroup H itself. That is. And a second property is that for any X and Y, which are elements of the group G, Y, if Y is in the coset XH, which it implies that the coset YH and coset XH are the same. So let me repeat this once again. So we have two elements X and Y of the group. Then we can construct two cosets XH and YH with two elements X and Y. And suppose if Y is an element of the coset XH, then it will so happen that this coset YH is exactly same as the coset XH. So that means if two cosets have at least one common element, that means all elements of the cosets are exactly the same. So the two cosets are the same. If one element is common to two subsets, the two cosets, then all elements in one coset are also present in the other, and vice versa. So that means the two cosets are exactly the same. Now, if it so happens that Y is not an element of XH, then the cosets YH and XH will have no common element. Okay, so I have constructed XH and Y is not an element of XH. It's different from the set of elements of XH. Then the coset YH and coset XH will not have any common element. So these are two parts of this property. The first one is that if there is at least one common element between these two cosets, then all elements are common to both cosets. And if this element Y is not here, is not one of the elements of coset XH, then there will be no common element between the two cosets YH and XH. That means the cosets of subgroup are disjoint unless they are the same cosets. So you have two different cosets, then they are disjoint. There will be no common elements of two different cosets. We now prove these properties. The first property was that if Y is an element of the coset XH, then YH and XH are the same. So let us assume that Y is an element of XH. And that means there exists an element of the subgroup H, let us call it HI, such that the element Y is equal to X times HI. And that is because the cosets of H with element X are given by the set of elements HI, where HI is an element of H. So if Y is an element of X, that means there will be one particular HI for which X HI will be equal to Y. Then for all elements Hj of the subgroup H, we can construct the elements YHJ, and that will be the element of the coset YH. They are given by YHJ, where HJ are elements of subgroup H. Okay, so take any Hj and construct the elements YHj. Now I can write Y as XHI. So this is equal to YHj is equal to XHI times Xj. But now because of the associativity property, I can take the product of these two first and then take the product of the result with X. But HIHj is an element of the subgroup H, because subgroup H should be closed under multiplication of its own elements. So HIHj is an element of H. So Y times Hj is actually X times one of the elements of H. So that means this quantity on the right hand side is an element of XH. So that means YHj is an element of XH. So for any HJ, any element Hj of the subgroup H, YHj is an element of XH. Which means that YH, which is a set of elements given by YHj, all of which are elements of XH as well. Now we can also see that the order of the group, so order of the coset YXH is simply the order of the subgroup H, and similarly order of the coset YH is also the order of the group subgroup H, and therefore order of YH is equal to order of XH. So all elements of YH are also elements of XH, and there are as many elements in YH as there are in XH. So that means the coset YH is exactly same as the coset XH. Now about the second part of that property. That is, if we consider an element that is not a member of the coset XH, then we should show that YH and XH will have no common element. So that means the intersection of YH and XH is a null set. And to show this, our strategy would be to assume that Y is not an element of XH, and then assume that YH and XH has a common element. Then show that this leads to a contradiction, which would then mean that it will not be possible for YH and XH to have a common element. So let us assume that Y is not in XH and that YH and XH have a common element. So if YH and XH have a common element, that means there will be an element HI such that YHI, and there will be another element HJ such that YHI is equal to XHJ. And that is because YHI is an element of the coset YH, and XJ is an element of the coset XH. So for some element Hi and some other element Xj of the subgroup H, the common element will be given by YHI here and Hj there. So both should be the same. So this is that property, YHI is equal to XHJ. And since this is a group, HI's inverse will also be there in the subgroup H itself. So you multiply from the right side of this equation with HI inverse. So I will have HI inverse equal to XHJ HI inverse. Now HI inverse is identity, then Y times identity is Y. So the left hand side becomes Y. And the right hand side is equal to X Hj Hi inverse. Now Hj Hi inverse. Hj is in H and Hi inverse is also in H. So this is a product of two elements of the subgroup H. And because of the closure property, this product should be one of the elements of H itself. So Y, that is the left hand side, should be equal to x times an element of H. So x times an element of H is an element of the coset XH. So that means Y is an element of the coset XH. So the assumption that YH and XH has a common element led to the requirement that Y should also be an element of the coset XH. But our assumption that Y is not in XH. So this contradicts the assumption Y is an element, Y is not an element of XH. And therefore, we see that if Y is not an element of XH, then YH and XH will have no common element. So their intersection should be the null set. We now discuss a theorem on subgroups, and this is called the Lagrange theorem. The Lagrange theorem on subgroup, and which states that the order of a finite group is an integral multiple of the order of any of its subgroups. It is easy to prove this, and for this we suppose H is a subgroup of the group G, and we also assume that the group of G, the order of the group G is given by small letter g, and the order of H is given by small letter h. Then the theorem can be stated in the following way. G, which is the order of the group G, order of group capital G, is equal to an integer n times small h, which is the order of the subgroup H. So the proof of this theorem. So H is a subgroup of order H of the finite group G. Now we note that every element of group G is in one of the cosets of H, and that's because of the following. We can, so for any element Y of the group G, we can construct the coset given by the coset YH, obtained by multiplying Y with every element of the subgroup G, subgroup H. Now H contains the identity element, and therefore when we take the product of Y with the identity element, we will get the element Y itself, because Y times E is equal to Y. Or in other words, the element Y is an element of the coset YH for any group H, because any subgroup H, because a subgroup should contain the identity of that group. And therefore, every element of the group G should be in one of the cosets. Now we make use of the other property of the coset, and that is the cosets are disjoint. So that means either two cosets can be exactly the same, or if we are considering two different cosets, there will be no common element at all. And therefore, we can choose a set of elements which we call as y1, y2, etc. up to yn. And y1 can be taken as the identity element itself. Now, we construct the cosets y1h, y2h, etc. up to say ynh. Remember, if we have taken y to be the identity element, then y1h would be identity times h, which would be h itself, the subgroup H itself. And we will choose y1, y2, y3, etc. in such a way that all these cosets are disjoint. So this can be constructed in the following way. Suppose we start with the subgroup itself. So that is actually equal to the coset E times H. Now we choose another element y2 of the group G, which is not an element of the subgroup. So we will get y2h. This is a second subgroup, second coset. Now these two cosets will have no common element because of the property that we just discussed. Because y2 is not an element of H. And then suppose, so this will be, there will be H elements here and H elements here. And suppose G contains an element which is not in either H or in Y2H. So choose one of those elements and call it Y3. So now remember, Y3 is not in H or not in Y2H. And we can construct a new coset, Y3H, which will again produce H elements. Now we see that Y3H and Y2H will be disjoint. And similarly, Y3H and YH will be disjoint. That is because, Y3 is not in Y2H or in H. And we can proceed like this until all elements of the group of the group G are exhausted. And remember, we can do this because every element of the group should be in at least one of the cosets, as we discussed earlier. So we can always choose a set of n elements of the group G such that YIH and YJH are disjoint. Further, since we have exhausted all the elements of group G by this, we can see that if we take the union of all these YIH, the cosets, this will be equal to the group itself. Because it will contain, this union will contain all elements of the group G, because any element of the group should be in one of the cosets. Further, while discussing this, we have noted that every coset contains H elements. So, and every element in coset will be distinct as well, because they are all disjoint. Now we see that there will be, if there are n such cosets here, and the union of n such disjoint cosets give the group G, then the number of elements would be H for each of the cosets, and therefore a total of n times H elements will be there. So the group G should contain n times H elements. So that means the order of the group G should be equal to n times H. And this is exactly what the Lagrange theorem says. Given any group, then the order of the group should be an integral divisor of the order of the group. So NH should be equal to, and n should be an integer, as we have seen here. Now, the integer n, which is G times H, is called the index of the subgroup H in the group G. Now, we prove an associated result which says that the order of every element of a finite group must be an integral divisor of the order of the group. Now, Lagrange's theorem says that the order of a subgroup should be an integral divisor of the order of the group. Now, here we are saying that the order of every element of the finite group should be an integral divisor of the order of the group. And it is easy to prove because order of an element is given by the following. Suppose A is an element and its order is given by n. Then A to the power n is equal to the identity element. Then we can consider the set of elements given by A square, etc. Then an minus 1 and an, which is E. And as we have already seen, this is a subgroup of the group, and this is an abelian and cyclic subgroup. Now, the order of this subgroup is n. So that means given an element A of order n, then it will form a subgroup given by a square, etc. up to an, which is identity, a subgroup of order n. Now, Lagrange's theorem says that the order of the group should be divisible by the order of any subgroup. Now, the order of this group is simply n, the order of the element in the group. And therefore, it follows that the order of the group should be divisible by the order of the element as well. Normal subgroups or invariant subgroups. Let H be a subgroup of G. Now, if for every element Y of the group G, the left coset given by YH and the right coset given by HY are the same, then such a subgroup is called a normal subgroup of the given group. Now, a normal subgroup sometimes is denoted by this symbol H, and we have this symbol denoting that it is a normal subgroup of G. A normal subgroup consists of complete classes of the bigger group. That is, if H is a normal subgroup of G, then this H contains complete classes of G. So that means you take any element of Hi of the normal subgroup H, then all elements that are conjugate to Hi are also in the subgroup H. So take all elements Y inverse Hy for all Y in G, and these elements should also be in H if H is a normal subgroup. And we will now show this. So suppose H is a normal subgroup. That means YH is equal to HY. So that means say for a particular element Hi of the group, then the element YHI should be an element of HY as well. One of the elements of HY. Say that element is given by some Hj times Y, because this is an element of the right coset. Okay, and one element of the left coset should appear in the right coset as well. Not necessary that the elements Hi and Hj here are the same. So one of the elements given by YHI of the left coset should be equal to one of the elements given by, say, some Hjy of the right coset. So this should be satisfied. Otherwise, for all elements Hi, for all element Hi of the group, subgroup H. So then we can multiply this equation then from the left with Y inverse. So when I do that, I have Y inverse Hi is equal to here, sorry, Y inverse YHI is equal to Y inverse HY. Or in other words, Y inverse HJY. Now, Y inverse Y is the identity. So, identity times Hi is equal to Hi itself. So, that means Hi is equal to Y inverse Hjy. Okay. So, given any element Hj of the group, then all elements of the type Y inverse Hjy is equal to some Hi, one of the elements of the subgroup H itself. But these are the elements of the class of Hj. So for any element Hj of the subgroup H, all elements of this type which are in the conjugacy class of Hj are also in the subgroup H. And therefore, we have proven that H should contain all the complete classes if H is a normal subgroup. And conversely, we can show that if subgroup H contains complete classes of a group G, then it is a normal subgroup of G. So if H is a normal subgroup of G, then H contains complete classes of G. Or conversely, if a subgroup H contains complete classes of the group G, then it is a normal subgroup of G. That is, its left coset would be equal to the right coset. And we now consider some of these examples of normal subgroups. Consider the subgroup we discussed earlier of the symmetric group of the square C4V. H equal to the set of elements E, C4 square, Mx and My. And we have already seen that this is a subgroup of, it's a proper subgroup of C4V. Now we see that E is always, the identity is always in a conjugacy class by itself. And that's because E is equal to Y inverse E Y for any Y, because E times Y is Y, Y inverse Y is identity. So if we construct the class of E, then that is simply the single element, the set with a single element E. So E is a class. Then we have also seen that C4 square is also a class, and Mx and My form a class. Please refer the earlier lectures to see that these are this is a class, this is a class, and this is a. So now H can now be written as the union of say E, which is a complete class, then C4 square, which is another class, and Mx and My, which is another class. So H contains complete classes of C4V, and therefore from the theorem that we just proved, it follows that this subgroup is a normal subgroup of C4V. Next, we consider a counter example. Another example in which the subgroup considered is not a normal subgroup. Consider the subgroup given by E, sigma U. It's easy to see that this is a subgroup because E, identity element, sigma U, E times sigma U is obviously sigma U, then sigma U square is E. So closure is there, associativity straight away follows from the associativity of C4V. Then inverse of sigma U is sigma U itself, and the identity is also. So this is a proper subgroup of C4V. And next we can see that this can be written as a union of two sets E and the set containing a single element sigma U. But E is a complete class, but sigma U is not a complete class. The class of the conjugacy class of sigma U is in fact sigma U comma sigma. So this is not a complete class. And from the theorem that we discussed earlier, you see that if H dash was a normal subgroup, it would contain complete classes. Now we can explicitly see here that it does not contain complete classes because this set sigma U is not a complete class. Therefore, H dash is not a normal subgroup of C4V. Next, we discuss quotient groups or factor groups. Let H be a normal subgroup of a group G, and we consider the cosets of H, and we denote them by K1, K2, K3, etc. So the set Ki denote the cosets of H. Now, it's a normal subgroup and therefore the left coset YH, say YIH, which we may denote as KI. And this will be exactly same as H times YI, the right coset. So we don't have to specify whether Ki are the left coset or the right cosets because left coset is equal to the right coset. Then we defined the coset multiplication. Consider two cosets, different cosets Ki and Kj. And then we define a new set with elements given by the product AB, where A is an element of the coset Ki and B is an element of the coset Kj. And remember, unlike in the class multiplication, here we keep only distinct elements. So if a particular element appears twice in this product, we will keep it only once. And this is the difference between the coset multiplication and the class multiplication. Now, we discuss some of the properties. Let Ki is given by the coset Xi times H and Kj by Xj times H for two elements Xi and Xj of the group G. Then the coset product Ki Kj is equal to we can write it as Xih dot Xjh, which is simply the coset of H with the element Xi Xj. And we prove this in the following way. So let us consider the product of Xih and Xjh, and the elements of this product will be the product of the elements of Xih and Xjh. So the elements of Xih are Xi, Hm for all elements Hm of the subgroup H. And similarly, the elements of Xjh are the Xj, Hn for all elements Hn of the subgroup H. So we take their product and form the set of elements obtained by taking products over all possible Hm and Hn. And we keep only the distinct elements here. So Xih times Xjh is simply Xihm, Xjhn, then Hm and Hn are the elements of the group H, and we keep only distinct elements appearing here. Now we note that HMXJ is actually an element of the right coset X HJ. But this should be this coset should also be equal to XJH. Okay, so that means XMXJ, which is an element of HXJ, should be an element of XJH also. So that means there should exist another element HP of the subgroup H such that this element Hm times Xj is equal to Hm times Xj is equal to, this should be the left coset, right? So H Xj times Hp, because this element should be an element of the left coset of the subgroup H with the element Xj as well. So there should exist an element Hp such that this element is equal to Xj times Xp. So then we can write Xihm times Xjhn is equal to, replacing Xm Xj by Xj Hp, we will have Xi, then Xj Hp Hn. Now we note that Hp Hn is an element of the subgroup H because of the closure. Now we have to consider all such elements for all possible values of hm and hn. For any hm and an element xj, there will be corresponding hp satisfying this relation that we wrote here. Now, as we consider all elements coming from all possible values of hm and hn, we should be considering all elements coming from possible values of hp and hn, which comes from the elements of the set subgroup H. Now, even for a fixed HP, if I vary Hn over all possible values of H, the product HP times Xn will produce all the elements of the subgroup H, which is nothing but the rearrangement theorem. So, if I consider all possible values of Hn here and Hm here, this quantity will keep producing elements of H only. And remember, in the coset product, we only need to keep terms that are distinct. So the elements of H keeps on coming up, but we will only retain distinct elements. So the distinct elements could then be considered as xi, xj times the elements of the group subgroup H. P, where HP runs over elements of the group. So that quantity is now nothing but the coset xi, xj, h. Okay, so I will state this once more. The elements of the coset product is simply given by xi, hm, xj, hn, with hm runs over all possible elements of H, and similarly Hn also runs over all possible element of H. Now this can be written as xj times some Hp, where Hp is an element of H. So that will now become this. But then here in this product we need to consider all possible values of Hm and Hn. So here all possible values of Hp and Hn. Now this is an element of H, and as I vary Hn, even if I keep Hp fixed, that will produce all elements of the subgroup H. So now if I consider all possible values of Hm and Hn, the elements of the subgroup H will appear many times, but since I am interested only in distinct values to be kept in the coset product, I only need to keep the elements of H only once. So the elements of this type that need to be considered are simply xi times xj times some hp, where hp are the elements of the group H. And we only need to consider each hp only once because we are only keeping distinct elements. But then if I do that for all possible values of H, then this is nothing but a coset xi xj times H. So that is the property that we needed to prove. So xih, which is a coset times the coset xjh, is simply the coset of H with the element xi times xh. Now the set of cosets of a normal subgroup H of a group G forms a group under coset multiplication. So the elements of the new group, which we call as K, are the cosets K1, etc., the set Ki of the normal subgroup H of the group G. So Ki are the cosets of the normal subgroup H. Now this set of elements under the group composition defined by the coset multiplication that we just defined, form a group. And that group is called the quotient group or the factor group of G with respect to the normal subgroup H. And the the quotient group is denoted by G/H. So we need to prove the claim that the set of cosets of a normal subgroup form a group. To see this, we first consider whether it satisfies the closure property. So the set of elements are AI, which are the cosets of the normal subgroup, and let us say that the elements are given by say XIH. So consider two elements of the set K. So XIH is an element of this set, and similarly XJH is also an element of the set of cosets of H. Then we take the product of any such cosets. So XIH times XJH, and from the property of coset multiplication, we have seen that this is simply equal to XI times XJ times H. Now Xi and Xj are two elements of the group, and therefore Xi Xj, the product, is also an element of the group, and therefore this is another coset of Xi Xj times H is another coset of H, and therefore this should be an element of the set of cosets K. Therefore the closure property is satisfied. Next we consider the coset multiplication, associativity of coset multiplication. Consider three elements Xi, Xj and XL, the group. Then we have three cosets with respect to the invariant subgroup H, XIH, JH and XLH. Now consider this product. First XJH dot XLH and then take the product of the result with XIH. But then this is nothing but Xj times XL times H, the coset given by that. And again, using the property of coset multiplication, this is simply equal to Xi times this multiplying H. So Xi, then within bracket this element. So Xj XL times H. But because Xi, Xj and XL are associative, then we can use that property. The group Xi, Xj, XL are the elements of the group, and the group multiplication is associative. We can use that property and write this as take the product of these two first and then take the product with XL. So that will be Xi, Xj times XLH. But then again, using the property of coset multiplication, I can write this as Xi, Xj times H dot XLH, where this dot represents the coset multiplication. And on the left hand side, this can now be written as XIH dot XJH dot XLH. And now from this is equal to this. Therefore, the coset multiplication represented by this dot associative. Now we need to think about the identity of this set. We see that the coset given by or coset corresponding to the element identity is simply the subgroup H itself. Now consider the multiplication of a coset XIH with this, the subgroup H. So XIH dot H, that is XIH dot EH, but using the property of coset multiplication, this should be equal to Xi dot or Xi times E multiplying H. But Xi times E is nothing but Xi. Therefore, this is equal to XIH. So, the coset multiplication of any coset XIH with the coset H, which is in fact the subgroup itself, is equal to the coset xi h itself. So this h, which is simply the coset with the identity element, which happens to be the invariant subgroup as well, is the identity of coset multiplication. So we have shown that the set of cosets of the normal subgroup also contains the identity element. And the next is the existence of inverse. And for any coset xi h, its inverse is defined by xi inverse h. That is because if we take the product of xi h with x inverse h, xi inverse h, then that should be equal to the product of xi with xi inverse times h. But this is nothing but identity. This is identity times h. But that simply gives the invariant set, the invariant subgroup h itself, which is the identity element as we have identified here. So we have shown that the set of cosets of an invariant subgroup, a normal subgroup, is closed under coset multiplication. Coset multiplication is associative. There is an identity under coset multiplication, which is the invariant group itself. And for every coset, there is an inverse, which is also a coset under the coset multiplication. So now we consider some examples. Consider the subgroup containing elements E and C4 square. And we see that this is a normal subgroup or the invariant subgroup of the group C4V. And that is because H can now be written as the union of the set E and set C4 square, and each of which are a class. Right? So this is a class of C4 and this is also a class of C4, and H contains complete classes, and therefore it's a normal subgroup. So now we consider the cosets of this subgroup. So let us now consider K1, which is identity times the subgroup H, which is H itself. Now we need to find another coset, and to find a distinct coset we have to choose an element of G, element of C4V, which is not in the first subgroup, first coset. So consider an element which is not in H, that is either E or C4 square. So we consider C4 and construct the coset C4H and call it as K2. When C4H is obtained by multiplying every element of H with C4. So C4 times E is C4, and C4 times next element C4 square is C4 cube. So we got C4 cube. So the second class is C4 and C4 cube. So one should also check that if I multiply this coset with the other element C4 cube in the coset, we will get the coset back. And the next one is choose an element of C4V which is not in K1 or in K2, so that we will get a new distinct coset. So it should not be E, C4 square, C4 or C4 cube. So I can choose the element mx and construct the coset mxh. So if I multiply the subgroup which is H is E and C4 square. So I multiply the elements with mx. Mx times E is mx, and mx times C4 square is my. So I get a new class, new coset. We can also convince ourselves by taking the product of K3, taking the product of My with H to see that that is exactly equal to K. So we haven't yet exhausted all the elements of the of the group C4V. In fact, we have considered E, C4 square. Then from K2 we have C4, C4 cube. Then from this K3 we have Mx and My. So there are two more elements remaining in this group C4V. They are sigma u and sigma v. So we choose one of these elements and construct the coset. So K4 equal to sigma u h. Again, multiplying E with sigma u, I get sigma u, and sigma u with C4 square, I'll get sigma 4v. So the fourth coset is given by sigma u, sigma v. Further, I can also take sigma v times h, and I will end up with the same. Now we see that I have exhausted all the elements of the group. Okay, and I have now got four cosets: K1, K2, K3, and K4. And in fact, the union of all of them is simply equal to the group G itself. Now, the quotient group with respect to H is given by C4V by H is the set of all cosets, which is K1. K1 was simply equal to H, then K2, K3, and K4. In fact, we can show by explicit multiplication that this form a group. For example, we can consider a few of those examples, a few of those cases. First, consider K1 dot K2. K1 is E C4 square. Now K2 is C4 cube. Coset multiplication is obtained by multiplying the elements and keeping only distinct elements. So first, E times C4 is C4. Then E times C4 cube is C4 cube. And C4 square times C4 is C4 cube. But I have already written that here once. Now C4 square times C4 cube is equal to C4 to the power 5, which is C4 to the power 4 times C4. C4 to the power 4 is identity. So this is simply equal to C4. That is already written there. So this product is simply C4 cube, which is K2. And we already knew this because K1 was identity. So let us consider a non-trivial one. So K3 dot K4. K3 was Mx, My, and K4 was sigma u, sigma v. Now take the product Mx sigma u and Mx sigma v, My sigma u, and My v. There will be four of them, four results, but only two elements coming from that. There will be C4 cube and C4. And please use the multiplication table of sigma for C4V from one of the earlier lectures to arrive at this result. And similarly, I can construct, we can check whether each of these cosets have their inverses under coset multiplication as well. For example, consider K2 times K2. So C4 cube times C4 cube. This is equal to, you have C4 times C4 is C4 square, then C4 times C4 cube is C4 to the power 4, which is identity, that is this. Again, this product, that is identity, and this will give C4 square. So the same thing. But this is nothing but the identity K1. And therefore, we see that K2 dot K2 is the identity, and therefore K2 is its inverse. And similarly, we can show that K3 inverse is K3 and K4 inverse is K4. So this is an exercise which can be easily done using the multiplication table of C4V, and convince yourself that all the properties that is required for this set being a group under quotient multiplication is satisfied.